Section 8.1 is sequences. It's the first of our chapter 8 sections, and it's the only one that we spend specifically on sequences because most of chapter 8 is about series. Now, what we ultimately would like to do is take a function like e to the x, and eventually something even more complicated, and represent it as a polynomial. Polynomials are very nice functions to do operations on. If we can represent our transcendental functions like e to the x, natural log of x, sine of x, cosine x, and all of these as in terms of polynomials, even if they are infinitely long, like this one is, there's infinitely many terms that need to be added here, we can still make use of that in approximation. And notice that we could easily integrate a function that looks like this. So that's more or less where we're headed. We want to be able to represent all our functions of calculus in terms of polynomials. Most of that is for an approximation purpose. Now, in order to get there, we need to talk about sequences first. So we'll build up quite a bit to get to representing e to the x and all of its friends as infinitely long polynomials. So first, we have a sequence. A sequence is a list of numbers, a1, a2, a3, an, all the way, and infinitely many of these. Okay, now the nth term is a sub n, and it's referred to as the general term. So, and it often holds the formula for, oh, well, what the sequence of what each term should be. Okay, so there's a general formula for sequences oftentimes, and we can use that to represent a sequence without having to write down infinitely many values. So the subscript values 1 through n and so on are referred to as the index of the sequence. So we'll often consider a1 through a3 denoted more so in this fashion. The sequence of terms a sub n, or a little bit more explicit, a sub n, where n is equal to 1 and so on through infinity. And n is always a whole number, positive integer. Okay, so write out the first 4 terms of the sequences whose general terms are listed below. So part A, our general term is 2 plus 2 over n, and the sequence starts at n equals 1, and it starts to count upward. So if that's the case, a1 is equal to 2 plus 2 over 1. See that in the formula here, and we get 4. a2 is 2, n is equal to 2, so it's 2 plus 2 over 2, and this is 3. And then a3 is 2 plus 2 over 3. N is 3, so it's 2 over 3. And we end up with 8 thirds. a4, 2 plus 2 over n is 4. So we have 5 halves, and so on. Now for the next one, negative 1 to the n plus 1 over 2 to the n for n greater than or equal to 0. So this sequence starts with n equal to 0, and it moves upward from there, counting positive integers. So a0 is when n is equal to 0, so it's 2 to the 0 and negative 1 to the 0. That leaves us with 1 plus 1, and we get a naught is equal to 2. a0 is often referred to as a naught. a1, n is equal to 1, so we have negative 1 to the first power, 1 over 2 to the first power, and that's negative 1 plus 1 half, so we get negative 1 half. a2, square the negative 1 to have a positive. 1 over 2 squared is 1 over 4. Add those together to get 5 fourths. And so on. Negative 1 cubed for a3, n is 3, so it's 1 over 2 to the third power. Again, we're negative. We have a negative 1 plus 1 over 8, and we get negative 7/8. So an interesting thing about this sequence, and we'll see this later on, is that its signs alternate, plus, minus, thanks to negative 1 being raised to a power of n. It's a really commonly useful tool that we'll use throughout this chapter. Okay, so find the general term of a sequence. This is more of a puzzle than anything. It's nice to have this skill handy, but we don't have to focus on it too much in this class. It's good to practice a couple though. So the general term of this sequence given right here, we're alternating in signs, so we'll handle that at the end. That's going to be a matter of taking negative 1 to a power. But well, the best thing I could say to do for one of these is to label these as first, second, third, fourth, so on, however many terms we're given. So we write a table with n equals 1 through whatever index we go up to. If we need more, we could propagate more terms and then try to help that, find the pattern from there. But the next step is to write each of our terms below that, and then we could look at how this number relates to these two numbers and do that for each of these pairs. I think once we have a decent look at this, we realize that in each one of these, the index 1 is the numerator, and then the denominator down here is the numerator or the index plus 1. So for each of these fractions, the top is n and the bottom is n plus 1. And that's how we come up with this portion of our general term, n over n plus 1. The top number is the same as our index. So a2, for instance, is n equals 2. So n equals 2 is the top, divided by 2 plus 1 is 3 in the bottom. So in order to handle our plus or minus, we know that it's -1 to a power of n. Now we note that we have a positive 1/2 to start with. So if we let that be the case for n equals 1, and this was just n right here, then it'd be -1 to the first power, which would be negative, and then this term would have to be negative. It looks like it alternates on the even terms. So all we have to do is change this exponent in -1 to make it even whenever n is odd. Well, the easiest way to do that is to add 1 to it. We could subtract 1 just as well. So now when we plug in n equals 1 to find a1, this is now -1 to the 1 plus 1. So -1 squared is +1. That's going to leave us with 1/2 after we apply the rest of the formula. Okay, so this works out. It's one way to get to these general formulas, these general rules. Remember that there are arithmetic sequences and geometric sequences. These are covered in pre-calculus before this class, so you might find some of that coverage in the book. You might find other tools for it online, or you might know it already. But definitely rehashing that can help you out with some of these. Now this sequence, 1, 3, 5, 7, and so on. This looks like it's all the odd numbers. Looks like we can represent all the odd numbers with, well, we'll let n count 1, 2, 3, 4 of these. So that's the index, a sub n, a1 through 4. And then 1 is 1, 2 is 3, 3 is 5. And it might be a little bit harder to spot this one, but if you look, you might realize that if we double each of these indices and then subtract 1 from their double, we get exactly these values here. 2 times 2 is 4, minus 1 is 3, 2 times 3 is 6, minus 1 is 5, 2 times 4 is 8, minus 1 is 7, and so on. So that's a decent way to just cite and come up with the arithmetic sequence, or sorry, the general formula, or the general rule. This is actually an arithmetic sequence. It's times the index plus a number. So that's a formula you're looking for. There are techniques to use this term and this n and its previous term and its previous index to come up with what this thing should be. But I'll let the reader look into that. Now, limits of sequences. This is important. This is what the main tool that we're going to use sequences for, in fact. So limits of sequences are somewhat related to limits of functions, or they're defined in a similar manner. A sequence a sub n is said to converge to a limit L that's written in this fashion. If for every positive number epsilon greater than 0, there's an m greater than 0 such that the distance in absolute value a sub n minus L absolute value is less than epsilon for every index that's greater than m. If no such m exists, then the sequence is said to diverge. Okay, so there's a lot of baggage here, a lot of things to understand that we might not completely get in this class as we move on, but it's a good idea to have at least a small notion of how this works. Hopefully we understand it fully. That's ideal. Okay, so let's suppose we've got exactly what was told above. We have the limit as n goes to infinity of a sub n is equal to L. All right, so our sequence looks like this: a1, a2, all the way out to am, and then am plus 1, and so on. Now, for this sequence that we've listed out here, this arbitrary sequence to have a limit, what this definition of convergence is telling us is that the distance between the sequence a sub n and its limit L has to eventually become small, less than epsilon. Epsilon's always thought of as being a fairly small arbitrary real number, but since it's arbitrary, it's just smaller and smaller and smaller. Um, A sub n and L need to be arbitrarily close together based on this inequality right here, above or below. So let's think about splitting this absolute value inequality apart, and it looks like this. A sub n minus L is greater than negative epsilon, and it's less than epsilon. But even better, let's isolate A sub n, add L to both sides as our last step, and now we get a better idea of what this convergence theory, this convergent definition actually is. A sub n is a sequence, these red dots here, and if it in fact has a limit L, then L plus epsilon is a little distance above L, and L minus epsilon is a little distance below it. Here's L itself. If this sequence converges to L, well, then it must get closer and closer to L. So what the definition tells us is that whenever we set any cutoff, epsilon, we can always find a point M or N, this capital N, and that would be about right here, for which all of these points are inside this little tube, this tunnel or whatever, this band around L. Okay, if we set epsilon smaller, which is possible because it's always going to be arbitrarily smaller, then we would cut off even further out, right, to ensure that all of our points are within this band. If we can do that for any epsilon, if we can always find an N, capital N or capital M, for which all the indices after this sequence keep us within a given epsilon band, then we know that this sequence converges. Okay. Now, in practical use, we won't really, appeal to the definition very much. We'll rely on some facts about convergence of functions and then a nice little mapping theorem between the two. For now, let's try to get some intuition. In the second video on this section, we'll cover the actual techniques that we use to prove these limits or actually really come up with them. So let's have a look at a few of these. We're asked to determine whether the following converge or diverge. If it converges, find its limit. Okay, so the first sequence is n over 2n plus 1, n equals 1 to infinity. So it doesn't hurt to experiment. It's the first time we've met one of these. So let's write some of these down. N equals 1, we have 1 over 2 times 1 plus 1 is 3, so we get 1/3. Do that for n equals 2, we get 2/5, then 3/7, then 4/9. Well, pause for a moment. Think about this. This is 1/3 is 0.33 repeating. 2/5 is 0.4. 3/7 I think is about 0.42. 4/9 is 0.44. 4 repeating. It looks like we're probably moving to 1/2. Okay, and here's maybe an explicit way to come up with this limit. Even though we don't have any limit laws yet, we'll see how to get around all this in the future, but let's just do what we would naturally do, and in this case it will work out. We'll see how and why this works later. If we want to find the limit as n goes to infinity of this sequence, let's just multiply the top and the bottom by 1 over n. Remember, we always do that for the numerator. We match the degree of the numerator. We find it, or the leading power term is n, or n squared or n cubed, whatever it might be. In this case, it's n. And we divide the top by n and the bottom by n. This is a form of 1, so it doesn't ultimately change our sequence term. And we do that, we get 1 over 2 plus 1 over n. This is multiplied by both of these terms in that denominator. Okay, now the limit as n goes to infinity of this is driving this 1 over n term to 0, and it's leaving these two constants with respect to n as 1 and 2. So this limit really goes to 1 over 2 plus 0, and then that's just 1/2. So ultimately, we will evaluate limits of sequences in this fashion, but just so we don't have to reprove all of our limit laws for sequences, these discrete functions, in other words, they only take integer whole numbers as their arguments that we plug into them, versus a continuous function that takes any real number. We're going to just map these discrete sequences over to our continuous functions in a subsequent theorem in these notes. We'll see that a bit later. For now, let's just keep getting an idea of, let's just keep learning how to handle these sequences sort of naively. So -1 to the n times n over 2n plus 1. The only difference between this and the first one is that now we're alternating signs. When n is 1, we have -1 to the first power. That's a negative. So then we get -1/3. When n is 2, -1 to an even power is going to make this positive. And then we just see that we have the same sequence as above, but just alternating terms. Now, there's a question about convergence, though. This thing, the negative terms are getting closer and closer to -1/2. The positive terms are getting closer and closer to +1/2. There's never going to be so if we had epsilon equal to 1/4, and we were trying to fit all of these points inside this smaller tube, and this was L, our limit in the middle, epsilon is 1/4 above L, something like this. This is just to see that definition. It's not exactly necessary to do this, but 1 plus and then L minus 1/4, we'd have trouble, right? Because we know that these points move a distance of 1 away from each other, or nearly 1 away from each other out here around whatever that limit could be, because they're oscillating. They're alternating signs, so they're bouncing around what would possibly be a limit. They'll never fit inside this tube and converge to L. Okay, so we found one such epsilon, 1/4, for which this definition of convergence won't hold, and that's all we need. There are no there's no index, no matter how far we go out in this sequence, that's going to make those dots get closer and closer to our limit L. Okay, force it to stay within that tube. So this one actually diverges, and again, maybe just the simplest thing is to say, because it tends closer and closer to -1/2 and +1/2. A sequence cannot have two different limits. Okay, so -1 to the n plus 1 times 1 over n. So another alternating sequence with a simple scenario, though, 1 over n, we just consider by itself. When you do that, you realize that 1 over n, as n goes to infinity, well, that limit is just 0. So now, even though this one alternates on the way there, you could write these terms out. You have +1, -1/2, +1/3, -1/4. But those terms are shrinking to 0. Their alternation of sign is just fine. They're alternating around 0 and ultimately getting closer and closer to 0. So this one converges to 0. Okay, lastly, 8 minus 2n, n equals 1 to infinity. We can just look at this one using our usual limit notation, even though we haven't formally introduced this, and realize that 2 times n, as n goes to infinity, is going to grow infinitely large. With the minus sign in front of it, 8 minus a number that's growing infinitely large is going to be -infinity. So this one diverges as well. So those are, informal ways of evaluating a few limits. We've introduced what a sequence is, and we defined the convergence of it. In the next video, we'll have a better tool for assessing convergence of sequences, and that's pretty much all we're going to cover about sequences for the rest of chapter 8. So be sure to check out that next video and learn how to formally assess convergence and divergence of sequences.